All right, let's do a couple center of mass problems next. One center of mass for a two-dimensional object and one for a three-dimensional object. The book does an example with a triangle as a two-dimensional object. Let's do a semicircle for our three-dimensional object. I could make it so the base or the diameter of the semicircle is on the vertical axis, but let's switch it around and make it on the horizontal axis like this. And let's say its radius is 5 centimeters. If that's the case, then I'd want to draw axes in here as well. Put this point on the semicircle, the midpoint of the diameter at the origin, say. The y-axis going upward like that. Radius is 5 centimeters. And I'm after the center of mass for this object, this two-dimensional object, which you could, if you want to imagine it to be like a thin plate of metal or something, you could do that. In order to do this in calculus 2, to find the center of mass, we need to assume the density is constant. If the density is not constant, you need multivariable calculus. For one-dimensional objects like thin rods we talked about on Monday, the density was a function, variable. Here, we're going to assume the density is constant. And we can use our typical letter, lowercase delta. This would be an area density, mass per unit area, because it's a thin plate, sometimes called a lamina. I love that word, lamina. Sometimes called a lamina. Effectively, we're treating it as a two-dimensional object. Of course, in real life, it would have some thickness to it. But for the purposes of modeling it mathematically, we pretend it's two-dimensional, and we think of the area as being in grams per unit area instead of grams per unit volume. Not going to specify what the constant is. Although if I do give you the mass, which I am going to do, we can figure out what the constant is. Assume the mass equals, say, oh, what did I do in the first class? I think 20 grams or something. Let's be consistent. Yes, I assume 20 grams. Okay, it's an assumption I'm making. I don't have to assume I know the mass, it turns out. But I'm going to go ahead and make that assumption anyway. The book does it in their triangular example. Okay, it's something we could do if we want. If I assume I know the mass, then I can figure out what delta is. I can figure out the density. For constant density, density equals mass per unit area here, not volume. So that's going to be 20 grams divided by the area of this semicircle. 1/2 pi r squared. Dividing by 1/2 is the same as multiplying by 2, so I get 40 over 25 pi. And by the way, the units for the bottom would be square centimeters. This would be in grams per square centimeter, and you can simplify that to 8 over 5 pi grams per square centimeter, and then we could approximate it. Eight divided by 5 pi about 0.5093 grams per square centimeter. And I'm assuming it's constant. This has got a uniform density. The atoms in this thin plate of metal are all maybe all the same kind of atom, same kind of metal maybe. And they're all approximately equally spaced, right? And in a metal, that's not so hard to imagine because it's typically kind of takes on a lattice structure. Although if it takes on a lattice structure, then it's got some thickness. All right, it's some sort of two-dimensional lattice of atoms. Just pretend. I don't know what would really go on in reality exactly. Mathematical modeling is about making reasonable assumptions, even if it doesn't quite match reality. You need to test if it matches reality or not. You hope it does as a first approximation. What about the center of mass? Because the the density is constant, by symmetry, the center of mass should be on the y-axis somewhere. This semicircle is symmetric about the y-axis. The x-coordinate of the center of mass should be 0. And I hope it's also intuitive. If this is 2.5 here, half the way to 5, that since in the y direction, most of the area, most of the solid mass is down near 0 compared to up near 5, that the y coordinate of the center of mass should be less than 2.5. Maybe that point is your center of mass. Call it x bar comma y bar. Or if you prefer, x sub cm comma y sub cm. Either notation is okay. Centers of masses are kind of like means in statistics. And that's why people sometimes use this notation. Other people just use the CM notation. And x bar should be 0 by symmetry. And you can just say that. Because the density is constant. So the problem now is to figure out what y bar is. Now there's a formula in the book. Let's go ahead and write the formula down. Well, I'll show it to you first. It's right here. But this formula is a little confusing in the way the book initially describes it. Let me go ahead and write it down. Y bar is going to be a ratio where the bottom is the mass, which we already know is 20. Though if we didn't know it, we'd have to figure it out by doing an integral, perhaps, at least, okay. You could avoid an integral in this context actually because you could do mass equals density times area because the density is constant. If the density were not constant, to figure out the mass, you'd have to do an integral, a double integral for multivariable calculus, in fact. Unless the density were constant along either vertical slices or semicircles centered at that point, then you could figure out the mass by doing a single integral. So the bottom is the mass, again, which we know we're given here is 20 grams. The top, you could describe in words as the total moment in the y direction. I don't know the origin of the word moment there. I keep telling myself I should look up why they call it a moment. It is related to moment of inertia, but why do they call it a moment there? Why are moments of inertia called moments of inertia? Nothing to do with time. I should look it up. I haven't yet. Maybe somebody's written an article about it. The book says that moment is the integral of y times delta times something it calls a sub y of y, dy. They write it initially here in the book as an indefinite integral. But of course, this has got to be a number in the end. So it's got to be a definite integral, right? Indefinite integrals are functions, families of functions if you include the plus c. Centers of mass are numbers. We really need a definite integral here. And it would be an integral. I think they didn't put it partially for typographical reasons and also partially because they wanted to apply to any situation. And in different situations, y is going to vary from different limits of integration. In this case, y goes from 0 to 5. But what is this thing right there? What is a y sub y? Question mark. For three-dimensional objects, they call that the cross-sectional area function. When you slice the three-dimensional object with horizontals, which slices perpendicular to the y-axis, which if the y-axis were going upward in 3 dimensions, which it's usually not, but if it were, it would be slices that are horizontal. If the y-axis were horizontal, it still would be slices perpendicular to that. But with two-dimensional objects, it's really not a cross-sectional area function. It's a cross-sectional length function. And the book does talk about that. The authors write that caveat in there. You just don't see it right away. But where in the world does this come from? I don't want to fully explain it, but let me give a hand-wavy justification for it. Really what you need to do is you need to think about slicing this with horizontal slices, thin horizontal slices, like that, of vertical width delta y. I'm after y bar, the center of mass in the y direction. So I do need to think about thin slices with small values of delta y. You really need to figure out the moment of this thin slice first. And the moment of a thin slice, what you're doing is you're really essentially trying to figure out the mass of the thin slice and multiply that times the distance, this distance here, of that thin slice to where y is 0, the x-axis. That would be the moment for the thin slice itself. Add up those moments to get the total moment, approximately. Let delta y go to 0 to represent that total moment as an integral like this. But y is the moment of this thin slice. How is it related to what you see there, the function that you're integrating? You need to first figure out its area. What is its approximate area? Well, it's approximately a rectangle, a thin rectangle. Area is base times height. Width times height. In the first class, I did call the width W. But I'll go ahead and do that here still. It's not exactly a rectangle, but it's approximately a rectangle with W times delta Y, base times height. But the width is the same thing as the book is calling the cross-sectional area. It's a cross-sectional length in this case. A sub y of y. W is the same as a sub y of y. That's what this, in a two-dimensional situation, that's what this symbol represents, is that length there. In a three-dimensional situation, if instead of a semicircle, this were a hemisphere, three-dimensional half of a sphere, then instead of a cross-sectional length, there would be cross-sectional area. And the area would be, think about slicing a hemisphere, would be a circle. You have to use pi r squared, as you've done before. What's the mass of that thin slice? I could call it delta M for small mass. Let me call it delta mass. The reason I'm calling it delta mass is because the word moment starts with M as well, and so I don't want to use two M's. The small mass of that thin slice is the density times its area. And its area, okay, so it's the density times the area. And the area is approximately this. And then the moment, the small moment of the thin slice, is to take that small mass and multiply by y. That's what the moment is. It's not saying the reason for the name moment. It's just what it is. It's y times the small mass. That'll be approximately y times delta times a sub y of y times delta y. And now you can kind of see where the integral is coming from. Add those moments up and let delta y go to 0, and you'll get the integral. Sum the moments and let delta y go to 0, and you'll get from this idea to the integral. But we still haven't completely figured out what to do yet, because we still need to figure out what W, the cross-sectional length, is. Still need to figure that out. We haven't done that yet. That's where the fact that this is a semicircle comes into play. We haven't used the fact that it's a semicircle other than to say x bar is 0. The equation of this semicircle is x squared plus y squared equals 5 squared. At a given value of y, the x coordinate can be found by solving for x as square root of 25 minus y squared. The x coordinate of that point right there. That's not w. I need to multiply that by 2. Right? X is this distance right there. W is the entire length of the rectangle, the width. W, which is a sub y of y, is 2x, but x is square root of 25 minus y squared. So now I can plug that in there in place of a sub y of y and do the integral. All right, let's do that as quick as we can. To find the total moment, and then we'll have to divide by the mass to get the final answer. Let me leave the delta in there as a delta and only plug in delta at the very end, because I'm also going to make a conceptual point when in doing so. So I'll just leave the delta as a delta. It's a constant. Times 2 times square root of 25 minus y squared dy. That's an easier integral to do than it looks like. Maybe I should have left the 2 in there. You don't have to do a trig substitution here. What could you do instead? It's actually an easy enough integral that you could, well, at least if you're good at calculus, you could, good at guessing integrals, you could guess the answer. You can do a substitution, an ordinary substitution, w equals 25 minus y squared, because then dw will almost be there for you. except for the minus sign. 2y dy is going to be negative dw. I can bring the negative sign out front if I like. I do need to change the limits of integration. Something a little funny here happens when y is 0, w is 25 minus 0 squared is 25. And when y is 5, w is 25 minus 5 squared is 0. That's not a mistake. Okay, I can remember I can get rid of the negative sign if I just switch those around. This is the same as delta times the integral from 0 to 25 of w to the 1/2. Let's see, integrate w to the 1/2, you'll get w to the 3/2 over 3/2, which is the same as 2/3 times w to the 3/2. And 25 to the 3/2 power is a simple number. It's 125. Because you take the square root of 25 first to get 5, and then cube that to get 125. 125 times 2 is 250. It looks like I got 250 over 3 times delta. Now I can plug in the delta. It was 8 over 5 pi. I figured that out like 10 minutes ago. I can reduce a bit. Looks like I get 400 over 3 pi. As what? As the moment. Not the final answer yet. That's the moment in the y direction. I got to divide it by the mass still to find the final answer. The mass I know is 20, right? That was given at the beginning. The mass is also the area times the density. It's also 25 pi times delta. The mass, yes, is 20 grams, but I also can think of that as 25 pi, which is the area of the semicircle, square centimeters, times delta, grams per square centimeter. And the reason I'm writing that is to emphasize that now when I find the moment, the y bar, not the moment, but the center of mass, I could figure it out with the delta in there, unspecified. And what would happen is these deltas would cancel. And so the conceptual point as I'm making is that the density, it doesn't matter for the center of mass because it cancels. As long as it's constant, it doesn't matter. Now, if it's not constant, then all this is out the window anyway. And you have to do multivariable calculus. But if it's constant, yes, it does affect the mass, and yes, it does affect the moment. But when you do the ratio, moment divided by mass, it cancels. And it doesn't matter. So I can either write y bar is 250 over 3 times delta over 25 pi times delta, and the deltas cancel, and get an answer. Or I could do it as 400 over 3 pi divided by 20. Either way is okay. Did I make a mistake? Is everything okay here? I do it as 400 over 3 pi divided by 20. That simplifies to 20 over 3 pi. This looks like it simplifies to 10 over 3 pi, so I'm feeling like I'm making a mistake somewhere. I'm not sure where my mistake is. There's got to be a mistake somewhere. In the previous class, I did get 20 over 3 pi as the final answer, centimeters, and that does simplify to, turns out 2.12 centimeters. That, I'm pretty sure that is the correct answer. This must be incorrect somehow. Oh, I know how. I know why it's wrong. The area here is wrong. It's actually 25 over 2. Because back up here, yeah, 25, 5 squared over 2 pi. 25 over 2 times pi. I just simplified it there and got a 40 instead of a 20. That's the problem. And then that should simplify to the same thing. Yeah, because that 2 can come up on the top. It'll simplify to the same thing. All right, so that's the y coordinate of the center of mass. Yes, it's less than 2.5. Next problem to do is center of mass for a pyramid. Pretend it's a pyramid in Egypt. The book does center of mass for a hemisphere. And I don't know the dimensions of the pyramids in Egypt, so I just made some numbers up. Let's say this is 50 meters. This is 50 meters. It's a square base. And let's say the height is 100 meters. I think the height is too small here. I'm not sure about the base. I think the pyramids are higher than 100 meters tall. I think. You're going to look it up? Michael? No? Okay. Let's just pretend it's 100 meters tall there. We're after the center of mass. So if you could grab the Great Pyramid and throw it in the air, it might twirl around, but the path would, the parabolic path would be followed by the center of mass. It's the idea of what the center of mass is good for. Of course, nobody would do that. By symmetry, well, if I put axes in here, say an x-axis going this way, maybe a y-axis going into the paper. Oh, and this is not a good drawing. And a z-axis going through the top of the pyramid. Pretend this line is vertical, or pretend it's, okay, this is a good drawing. Pretend the tip of the pyramid is more like there. By symmetry, the x and y coordinates of the center of mass are going to be 0. If this is a constant density. Assume constant density. Delta, this time in units of mass per unit volume, not area. Say kilograms per cubic meter. And this time I'm not going to bother saying what the mass is ahead of time. And I'm not going to figure out delta. I'm just going to figure out the center of mass. And just like before, the delta will cancel. The formula in the book, well, okay, x bar, y bar are both 0. So the only question is, what is z bar? By the way, mathematicians almost always make z's with little lines through the middle, because if you don't, it sometimes looks too much like a 2, unless you always make your 2's curly, but not everybody does that. When I was young, I always used to make my 2's like that. But then when I became a mathematician, I switched to that. Also, when I was young, I always used to make my w's like that. But then when I became a mathematician, then I said that was an omega, and so I made my w's like that. It's an omega, not a w. All right. The formula says Z bar is going to be a ratio where the bottom is once again the mass. And the top is the total moment in the Z direction. Z is going to go from 0 to 100 here. It'll be Z times delta times A sub Z of Z, where A sub Z of Z is going to be the cross-sectional area this time, not length, when I slice this with horizontal slices perpendicular to the Z axis like this. And those are going to be squares because it's a square base. To figure that out at a given value of Z here, I need to figure out the side lengths, call it S. How can you figure out S? I'm going to show you two ways. One way is you could use similar triangles. You could imagine you're looking at the pyramid head on and it looked two-dimensional. Two-dimensional picture like this. There's two similar triangles in there. There's the big triangle and there's the small triangle. They're similar. S is this horizontal distance there. That's S. That's supposed to be an S there. I know it's small. That's S. Let's draw a vertical line through the middle here as well. It is an isosceles triangle. This distance, let's call Z, because it does correspond to the Z in the picture. Since the entire height is 100, that means this distance right there is 100 minus Z. And again, my two similar triangles are the big purple triangle and the smaller red triangle. Similar triangles implies that the ratio of corresponding sides, then the side down here is 50. In this case, 50 over 100, for example, equals S over the height of the smaller red triangle is 100 minus Z. So S is 1/2 times 100 minus Z, which is 50 minus 1/2 Z. You also could figure it out by realizing that S depends on Z in a linear way, just looking at the picture. And when Z is 0, S is 50, and when Z is 100, S is 0. So you could graph S as a function of Z. S is going to be 50 when Z is 0, and it's going to be 0 when Z is 100. And so its graph is that line, and the equation of that line you could figure out because the slope is negative 1/2 and the y-intercept is 50. And so the vertical intercept is 50. S would be 50 minus 1/2 Z, just like I got down there. Therefore, the cross-sectional area function is S squared is 50 minus 1/2 Z squared. I'm gonna square that in my head by FOIL. In my head, 50 times 50 is 2,500. Outside times outside is going to be negative 25Z. Also inside times inside will be negative 25Z. And then last times last will be 1/2 Z squared is 1/4. 1/2 quantity squared is 1/4 Z squared. Let's have Mathematica do the integrals for us to save some time. And I did mean to say integrals. You only see one integral there, but we actually have to do two integrals. Because I didn't specify the mass, I got to do an integral for the mass. The density is constant, so the mass is going to be the density times the volume. But I got to do an integral for the volume. Hey, but we've done this kind of integral before. Just integrate the cross-sectional area function. That'll be the integral for the mass. And then I've got to multiply by delta. Although I'm not specifying delta, and that's going to mean it won't matter. It'll cancel. So AZ of Z again is this. Integrate that. Which you could certainly do by hand, no problem. Get 250,000 over 3. That's the volume, cubic meters. Multiply that by delta, whatever delta is, and you get the mass in kilograms. For the moment, I need to integrate this thing times Z times delta technically as well. But again, the delta is going to cancel. That one gives 6.25 million divided by 3. So to summarize here, Z bar is going to be 6.25 million divided by 3 times delta technically. That's the moment. Divided by the mass, which is going to be 250,000 over 3 times delta. The deltas cancel, the 3's cancel. You're left with 6.25 million divided by 25,000. Can I do that in my head? Or 250,000. Can I do that in my head? 25? Yeah, okay, 25. Which makes sense. The pyramid's 100 meters tall. This is in meters. 100 meters tall. The bulk of the mass is under 50 meters tall. You should expect an answer less than 50. Happens to be 25. Doesn't always come out so nice. Okay. Anything that can be clarified here? I am, what's the word? Shoving some things under the rug here. I'm not really explaining the derivation of the formula for center of mass. It is in the reading. They do it in the discrete situation first when you've got point masses. They talk about the law of the lever, balancing a seesaw and a fulcrum and generalizing that idea. I mean, technically speaking, you need to verify centers of mass, even for one-dimensional objects, experimentally. You got to make sure the math makes sense, but has been verified experimentally.